Welcome to the lectures on modern digital communication techniques. So far what we have done is very interesting, and we are standing at a juncture where we could review what we have done. It is a very interesting juncture that we are standing at, because now we could evaluate the different schemes that we have studied, as well as benchmark them against a certain performance, so that it helps us in doing an exact performance comparison. So, looking back at some of the schemes that we have studied, we could say that we have looked at situations where k, which is the bits per symbol, is one of the important factors which is used to choose the constellation size, which is m is equal to 2 to the power of k. So, as k increases, we have seen that m increases. We stated that if t is the symbol duration, so the number of bits per symbol duration that is sent is t upon k bits per second. On the other hand, we have also seen that if there is a minimum Euclidean distance between two constellation points, then we found that probability of error is proportional to the q function of square root of some constant, let us say c, and d mean squared. So, what we see is that and d min is somehow related to E average, which is the average energy. So, what we see that there are at least 3 independent factors which are available in order to choose a particular size of constellation. We have also seen that when we studied QAM, there are several possibilities of choosing constellation, even though the constellation size would remain the same. For instance, this could be one choice of constellation that we saw, and in contrast there could be another choice of constellation. What we discussed was something like this. What we figured out that even if in these two constellations we maintain the minimum Euclidean distance as same, which means the same probability of error, and even if we have the same average power in these two constellations, still we stated that this constellation may be preferred because of lower peak to average power ratio compared to this. So, there are several criteria based on which you would be able to choose a constellation. And we had seen in general for constellations like PAM and QAM, as you have EB by N naught on x axis and you have the probability of error on y axis, and let this be one of the probability error curves. So, as we increase m, so if m is equal to 2, as we increase m equals to 4, the probability of error curves shift to the right, which means that to maintain a certain probability of error, as we increase the constellation size, that means as we increase the bits k, our bits per second increases, but the minimum required SNR or EB by N naught also keeps on increasing, right. And in another way, you could say that if we keep EB by N naught constant, as we keep increasing the size of the constellation, the probability of error keeps on increasing. So, this is equal m equals to 4, this is let us say m is equal to 8 and 16 and so on and so forth, right. So, as we keep on increasing m, that means as we keep on increasing k, by keeping same EB by N naught, the probability of error increases. And we explain this in the form that if there is a certain constellation and we want to keep the same average energy, however, we want to increase the number of constellation points So, then what we get is the constellation points come much closer compared to the previous case. So, the constellation points coming closer means d min become smaller, which means probability of error becoming larger. So, that is what we have here. Whereas, when we studied orthogonal signals, what we found is that the probability of error curves behaved in a different way. So, if this was the probability of error for m equals to 2, for m equals to 4 it could have been here, m equals to 8. So, we could roughly say m equals to 4, m equals to 8 and so on and so forth. And we did discuss that what would happen if we keep on increasing m, right. If we keep on increasing m, is there a bound that we reach on gamma bar, was one of the questions. And but when we reach that bound, what we could actually get is make probability of error go to almost 0. But in this case, what we had, as m increases, if we think of Emery orthogonal signaling, this implies that the bandwidth required also keeps on increasing. So, in one case, if we have to reduce or keep probability of error constant while we keep increasing m, we need not spend extra energy, extra power, we can simply keep on increasing the bandwidth. Whereas, in the other case, if we have to increase the constellation size, that means increase the bit rate, we have to spend more power. That means, if I have to keep the same error probability and have to increase this the m value, I have to keep maintaining a higher E b by n naught. This is E b by n naught, and since n naught is constant, it is in terms of increasing higher E b. So, in one case your requirement on E b should go up as m increases, in the other case the bandwidth requirement goes up. So, here bandwidth is constant and in this case you can say E b is constant. So, we have two different possibilities, and of course, there are different variations on the error probability. So, at this stage it might be important to discuss that how do you compare the performance of these schemes in a fair basis. So, to do that there has been a very important contribution from a very eminent contributor, in the sense the father of information theory, Claude Shannon, who proposed or who developed the expression for an important term known as channel capacity. So, we are going to discuss a bit of channel capacity in this particular lecture, and the aim would be to get an insight into how the channel capacity comes into play and what is the consequence of channel capacity in terms of the performance of a digital communication system. So, however, when we are studying channel capacity, we need to, ideally speaking, start off with the basics of probability theory, asymptotic equipartition, and build up a lot of theory in order to understand the tenets of capacity, which is practically a full course on information theory. So, since we do not have the luxury to go into those details, we will give an overview of how do we arrive at the expression, what is the meaning of the expression, and how we can use the expression in the study of digital communications. So, with this let us proceed into the study of channel capacity as is famously known. So, when we study channel capacity, generally we have to first study the different kinds of channel that may be available. So, one of the channels that is of our interest is the binary symmetric channel. The binary symmetric channel is one where of course, we consider additive white Gaussian noise, we will always consider additive noise, and this kind of channel, the name already describes certain things, that means it is telling is a binary channel, right, and it also says it is a symmetric channel, right. So, before we go into the description, let us see that how it is built. So, as it says, it includes the modulator and the demodulator. So, if we remember, in the modulator we had the g of t and we had the Sm of t, right. In the demodulator, again we would break down the received signal r of t, we would break down r t into its components, followed by, that means we would break it into components vector r, from which we are going to get the choice of the waveform that could have been transmitted. This is what was available in the modulator and the demodulator. So, now it says that we have to include this in the channel. So, I would like to remind you at this point, in the initial parts where we studied layering and breaking down into smaller components, we did say that you could view the channel at different points of the transmitter chain. That is, you could view the channel as a medium which carries electromagnetic signal, if you are looking at the channel from the perspective of from the output of the antenna, and if we slowly go inside into the transmitter, we come to a point where we look at symbols, that means the output of the symbol mapper goes into the channel. So, we have symbols going into the channel and symbols coming out of the channel. So, that means the up conversion is part of the channel model in that case. But here we go even backwards and we say that the symbol mapper or the modulator is also part of the channel. So, the interface and layering that we discussed, if you remember that, we were in a situation where the bits go into the symbol mapper and at the receiver bits count out of the detector, because the job of the detector is to select Sm star. Sm star means star indicates the particular result, one of the Sm. So, once you detect the particular Sm, you can easily identify the k bit sequence which map to it, because if this is your constellation and this is the detected symbol. So, definitely this symbol has a bit map which could be a 0 1. So, the output of the detector is 0 1, right. So, that means what we have is or let us say if this is detected at the receiver. So, the output could be 1 0. So, what we have is input into the system is binary bits. So, that means binary digits, and output is again binary. So, we are at the binary interface, right. So, when we are at the binary interface, what we have is a bit sequence. So, we will use this, that means zeros and ones goes into the symbol mapper. So, we construct the channel out of that, it goes through the channel, passes through AWGN and demodulator, detector, and again it produces a sequence of zeros and ones, right. So, when it does so, what we have is a 0 as the input and the output could be a 0 or the output could be a 1, because we have stated the detector must choose something. The detector cannot stay without choosing a particular solution. Similarly, when a 1 goes into the system, the 1 may be detected finally as a 1 or it could be detected as a 0. So, this is the abstract form of the channel model. So, at some point you may remember there is noise which is getting added to the signal. So, the received signal R of t is made up of SMT plus noise. So, if we think of components, then R k of t is equal to S m k of t plus n k, right. So, that means there is a signal component, there is a noise component, and we have stated many a times. Let us consider the BPSK model where we have d and minus d. Suppose I map this to 1 and this to 0, and we have selected this for transmission. So, if we have selected this for transmission, then if the noise is strong enough minus negative value and it shifts to this side, then the MAP or the ML detector would detect the received signal as possibly a minus d or a 0. So, in that case an error happens, and this is what we have discussed earlier. So, and we have calculated probability of error given S1. So, for BPSK this turns out to be the probability of bit error. That means, the probability that when a 1 is sent it becomes a 0. So, probability that a 1 is sent it becomes a 0 is p. Similarly, probability of 0 becoming a 1. So, how we calculate it is by considering the conditional PDF, and the probability of 0 becoming a 1 is the area under this curve, and probability of 1 becoming a 0 is area under this curve, right. So, probability of 0 becoming a 1 is p. So, now because of symmetricity, that means 0 becoming 1 and 1 becoming 0, we have a symmetric channel. Because there is binary input, binary output, we have binary symmetric channel. So, probability of 0 remaining a 0 is 1 minus probability of error, which is probability of being correct. Probability of 1 remaining a 1 is 1 minus probability of error, which is 1 minus p. So, now we have the situation which maps a 0 to 0 and 0 to 1 and a 1 to 0 and a 1 to 1. So, these provide the transition probability values. That means, probability that I get a 1 when a 0 is transmitted is equal to I get a 1 when a 0 is transmitted is p, and probability that I get a 0 when a 1 is transmitted is p. Probability that I get a 1 when 1 is transmitted is 1 minus p, and probability that I get a 0 when 0 is transmitted is 1 minus p. So, whatever we reflected here is shown in this particular setup. So, probability that I get a 0 when I sent a 1, I get a 0 when I sent a 1 is same as the probability I get a 1 when I have sent a 0, right, and that is equal to p. Similarly, the probability of the output remaining same as the input, is the output remaining same as the input, in both the cases is 1 minus the probability of making an error, and that is probability of being correct, which is 1 minus p. This is exactly that what we have written on the paper. So, this is the basic model, and this model we do use in some of the calculations. So, this is for mainly for you to know. So, just a side note over here, we are discussing this for sake of information, so that our understanding is complete, but we will be mainly interested in the final expression as we have announced in the previous lecture. So, moving further, the other important channel of interest is the discrete input continuous output channel. So, as the name tells you, the input is discrete, and clearly we have discrete input because our input takes values, let us say minus d or plus d in case of binary pulse amplitude modulation. In case of quaternary pulse amplitude modulation, we will have 2 additional amplitudes. So, these are discrete inputs. In case of QAM, it is discrete input. In case of PSK, it is discrete input. So, we do have discrete input, right, and continuous output simply because if we send let us say d which is SMT, which is a value of D, what we receive is plus noise, what we receive is noise. So, when a discrete value gets added to noise, which is a continuous valued signal, what we have the situation as discrete input, but continuous output, discrete input, continuous output. Okay. So, this kind of channel is this, and it is very easily characterized by the modulator alphabet x 0, that means, they are discrete symbols, right, and the output of the detector is unquantized. So, that is what we have. The channel is characterized by the discrete input x and continuous output y. So, it is simply stating that you have these variables x and y, one at the input, one at the output, and you have the set of conditional probability density functions which define the channel. So, simply we have already discussed that thing here, we have already discussed it in the model that we have drawn here. This is one of the situations. So, if I am taking R k, I am already taking a discrete input, continuous output, but if I am taking the discrete output, that means the decision output, I go to a discrete input, discrete output. So, in case of Emery, you may remember the situation was so we have 0 d 3 d minus d minus 3 d. So, the conditional PDF is if 3 d is sent, probability of receiving anywhere in this is given by this particular curve. If d is sent, probability of receiving the signal along this is given by this PDF. Probability of, if you send minus d, this y axis is the probability density function axis, right. And then if you have to convert this to a discrete output, you have to calculate the probability of error. So, in that case, if minus d is sent, you will be calculating this area. However, what we have is probability of received signal given 3 d as the send, right. So, that means, we are here, it is given by the set of conditional PDF. So, it is given by the set of conditional PDF. So, these characterize, now you can clearly understand that these conditional PDFs carry information about the channel, that means, they are characterizing the channel. So, the noise impact is characterized into these transition probabilities. So, if we would have gone to the previous slide, here we find that these transition probabilities, these are the transition probabilities, and these are clearly due to the noise effect, which you can easily see that because of noise you have a certain probability of error. So, probability of error, in this case it is probability of bit error, which is equal to p. So, the noise is getting translated to a transition probability. So, similarly, in this case as well, the noise is affecting the conditional probabilities, right, and this, and in an AWGN channel you have the simple model y equals to x, the transmitted signal, no distortion due to channel, plus there is noise getting added, and G is 0 mean Gaussian random variable with variance of sigma squared, and for all situations we have taken this to be n naught by 2, right. So, that is what we have seen before, and the conditional PDF, we are used to this expression. So, there is nothing new in this expression, 1 by root 2 pi sigma n e to the power of minus y is the received signal. So, what we had used earlier was, what we had done earlier is we had used r minus s m t, rather we had used r k minus s m k squared upon n naught. This is what we had used, right. So, this is the same thing that you see over here, you do not see anything different at this point. Okay. So, the next kind of channel what we can think of is the waveform channel. So, in the waveform channel we have to consider a channel bandwidth W and an ideal frequency response. So, in the earlier case also we had the ideal frequency response. So, it says that it has an ideal frequency response Cf equals to 1 within this bandwidth W. So, that means you have a response like this. Okay. So, this is W and this gain is 1, and x t is band limited and y t is the corresponding output. So, this is the band limited input because you have a certain bandwidth W and y t is the corresponding output. So, again you can see in additive wide Gaussian noise it is given by. So, here x t takes continuous values, y t takes continuous values. So, it is a continuous input, continuous output, and hence it is known as the waveform channel. And of course, n t represents the sample function of additive wide Gaussian noise process. So, we expand x t, y t and n t into its complete set of orthonormal functions, which we have already done before. We have been doing it throughout. So, y t is equal to expansion in terms of f I t's, y I t's are the components, same with x I t's, and you could write. So, it is very small over here. Here we write that the functions are orthogonal to each other. So, finally, what we write is that y k, or if we use our earlier notation, we have r k, that is the kth component, is equal to m s m and its kth component plus noise and its kth component. So, how you get it? You simply get it by projecting r on f k t integrate from 0 to t, which is equal to 1 upon w dt is equal to r k. That is how you get it. And you remember that f k and f m are orthogonal to each other. So, what we also have is f k f m 0 to t dt is equal to 0. Of course, this is a function of time, this is a function of time. So, these are some things which we have been using, right. So, this is classified as a waveform channel. The main difference is input is continuous, right. Okay. Right. So, now in such conditions what we had seen is that these f k's being orthogonal, because these f k's are orthogonal, what we found is that k not equal to m. So, rather it is important to write it as delta m k, right. So, equals to 0 for k not equal to for k equals to m, right. This is the whole thing. So, what we get is that the signals r k, which is equal to s m k plus n k, are independent, because n k and n m, what we had calculated earlier is that they are uncorrelated. If they are uncorrelated, we know they are Gaussian and therefore, they are independent. So, r k given s m k is a Gaussian random variable with a mean s m k, and again the same applies, these are independent, these are uncorrelated. So, again they are Gaussian, uncorrelated means independent. So, at the receiver, if these are the components, so the joint distribution of the received components given the transmitted signal is equal to the product of the marginal conditional distributions. So, simply because of orthogonality criteria that we have. So, these are some of the things that we use. So, since we know this expression, already, 1 over root 2 pi sigma n e to the power of minus r k minus s m k squared by n naught. So, this is what we use. So, now what you will get is you are going to use all these corresponding expressions, you are going to get a product of them, and hence you will be able to compute the necessary things. So, we stop this particular lecture here, and we using the channel models that we have developed, we will take a look at the channel capacity, from which we will finally take a look at the performance comparison of the different communication systems. Thank you.